Hello, this is Ramhan. I am working as head of department at Government Polytechnic, Mahabubnagar. The topic we are going to look into is the semiconductor diode. The subtopic currently we are looking at is the energy level diagrams of the conductors, semiconductors, and insulators. Let us recap what we have learned so far. We have seen the classification of the electrical materials. We have also learned about the electrical properties of the conductors, semiconductors, and the insulators. Now let us see the objective of our lesson. On the completion of this topic, you should be able to understand the energy band levels in the solids or in materials. Then we will be in a position to understand the conduction band and the valence bands in the materials. We can also have a good idea about the energy level diagrams of the semiconductors, conductors, and the insulators. Now let us see the energy bands in the solids. Here it is. So this is the first orbit, and there is a forbidden gap. Another band of energy level, that is n equal to 2, and you can see some forbidden gap likewise. The range of the energies possessed by the electrons is known as the energy band. It's a group of electrons having a particular level of energy. They are clubbed together, and that is called as a band. So these, you can see, there are different levels having different energy band levels. The energy bands are separated by an energy gap, which is often known as the forbidden energy gap. The important energy bands in the solids are like this. We can see they are lower field energy bands as a reference. Then we have a valence band. Then the range of the energies which are possessed by the valence electrons is known as the valence band. Now we also have a conduction band. So here the range of the energies possessed by the conduction band electrons is known as the conduction band. And you can see that there is a gap in between these two energy bands, and that is known as the forbidden energy gap. The gap between the energy bands is known as the forbidden energy band. Now energy bands in insulators. So you have a reference energy band which is low energy field. Then you have a valence band. Then you have a conduction band, and we're talking about the insulators. So in between there is a large forbidden gap, and normally this forbidden gap is expressed in terms of electron volts, and for the insulators it is 6 electron volts. And let us see into the energy bands in a insulator. The valence band here is full, and the conduction band is empty. So that's the reason why the insulators don't conduct any electricity. They are not at all carriers of current or electrons. There is a large energy gap, more than 6 electron volts, between the valence band and the conduction band. Now let us see the energy bands of a semiconductors. That's our reference level, which is lowly filled energy band. You have a valence band and a conduction band. Let us see how much the gap here is. So you can see that there is a forward gap, and how much is that? It is about 1 electron volt, and this forward gap is measured at 0 degrees Kelvin. So and in this energy band of a semiconductor, you can see the valency band are partially filled valence band and also partially filled conduction band. It is to be noted, we have to remember this is important. The energy bands in this, let us see about the energy bands in the semiconductors. So you can see that the partially filled valence band, and there is partially filled conduction band, and the electron gap between the two bands is forbidden gap, and that is just 1 electron volt. And so at 0 degree Kelvin, it is going to act like a insulator. That means on its own it cannot work as a conductor. So let us see the energy bands in a semiconductors. What happens here? So you have a valence band, you have a conduction band, and a forwarding gap of 1 electron volt. Now, on application of an external energy equal to 1 electron volt, a covalent bond breaks and an electron crosses the gap and enters the conduction band, leaving a hole in the valence band. See, why am I talking about this? Because the electron gap between two energy bands, that is valence and the conduction band, is very less. It is very marginal, and it can be overcome by electrons by applying a little external energy. Now here we can see that the energy required to be external applied is only the 1 electron volt. So let us see what happens. So you are applying an energy externally onto an electron into a bond which is there in the valency band. Now what is happening here? Let us see. So you have applied an external energy, so let us see what is happening over there. Yes, you can see that the covalent bond is breaking and 1 electron is flying, able to travel and sit comfortably in the conduction band, leaving a hole behind. So an electron lost is normally denoted as a hole or denoted by a positive charge at the source point. So that is now adding up to the free electron in the conduction band. So what happened now? So this semiconductor, which was not having much quantity of electrons in the conduction band, are able to gather a few more electrons from the valence band. Hence now it is going to act like an conductor after small external voltage has been applied to it. It can be any form of energy, heat, electrical, or light. See, so that is denoting a hole in the valence band. Now let us see the energy bands in the conductors. You have a valence band, you have a conduction band. Here you can see that the two conduction band and the valence band are overlapped, so you don't see any forbidden gap. So there is a overlapping of so much bit in a conductor. Now let us talk about the energy bands in the conductors. So the valency and the conduction bands are overlapping each other in a conductor. There is absolutely no forbidden gap or no energy gap in between these two materials. Now let us summarize what we have learned so far. So in this we have discussed about the following topics: about the energy bands in solids, about the valence band, about the conduction band, then the forbidden energy gaps or bands. Now let us see what we could remember in a quiz. The energy gap between the valence band to the conduction band in a conductor is 1.5 electron volt, 15 electron volts, 0 electron volts, or 10 electron volts. So that is about energy gap or the forbidden gap in a conductor. How much is that? There is no forbidden gap. There is overlapping of the conduction of the valence bands. Now what is the energy gap between the conduction band to the valence band in a semiconductor material? 1.1 electron volt, 0 electron volts, 10 or 15. How much is it? It is 1.1 electron volts. So a small energy to be applied externally for the semiconductors to become as conductors. Now let us see into the frequently asked questions from the topics we have covered. Explain energy levels in the solids. Explain the valence band and the conduction band in solids. Discuss about the forbidden gaps.